This is now being recorded. Please will you mute if you're not talking. Also turn off the camera if you're not talking, because there's so many of us. It does slow the bandwidth down for people on a slower connection. So not as urgent as muting, obviously, but yeah, it'd be good to turn the cameras off. If you have any questions, as I said, please put them in the chat. Or if it's too long, just say, you know, I've got a question for so-and-so, what's the main topic? And then raise your hand and we'll try and sort the admin out to get you to ask the questions. And as I said, please introduce yourself in the chat so we can get through this quickly. Any questions?
No.
Okay. So we'll dive into the challenges facing federated PLM. So this is a series of slides that I've based on a presentation given at PDT last year by my late and very much missed colleague Nigel Shaw. So people may have seen some of these colleagues. I have pulled them around, cut some out, but you may have seen them before and probably presented a lot better by Nigel last year. So yeah, so this is about what are the challenges? Just a quick reminder, or just think back to what is what is a link? So this is just some simple HTTP links. Obviously things have moved a bit, but when we started on the internet, let's get this thing. It is most basic. A link is just an identifier. It's a link to something, but it doesn't actually tell you what it is. It's just, here is something. It could also be a logical address for something where you can find out more information. But again, it doesn't actually tell you what is at that address or what sort of address it is and what's at the end of it. Another thing a link can be is a relationship between two things. So it's usually one way, but it could be two-way. But again, the simple HTTP does not tell you what that link, what that relationship actually means. And the fourth type of link is a service type of link. So when you it's basically used to trigger behavior and return a response. So rather than just going and finding out information or opening something, it will actually return a response. But again, simple HTTP does not tell you what that thing does. It doesn't tell you what you should send, what you're going to get back, what it actually does. Obviously, these things are being addressed. I've just listed some here. Of some of the things that are addressing these questions, and this is the sort of topic, sort of subjects that's part of the second topic, interfacing patterns and standards for addressing this type of link. So that's just to give an idea that there are different types of link out there that we need to handle. So what does that mean for engineering? So a lot of the stuff on the internet is not engineering data. It's other types of data. But for engineering, what could we use it for? One of the main ones is to maintain traceability across tools and across disciplines without having to copy paste everything. So instead of just copying it across from one tool to another, you just link to it, and that would be great. Another key one is to know where the source of something is. So again, if everybody is using the same value of something, then for example, in an analysis, then you will all know you're using the same source. So this gets down to sort of single source of truth type things. Other ones for requirement management, linking requirements to the actual design artifacts. So this gets very interesting when you start getting to change management. If a requirement changes, or what designs does it affect, or if a design of something, of a component changes, where is it used in an assembly? Those sort of things get very, very useful. Configurations, being able to link make a configuration across multiple platforms, it would be very useful. So instead of copy pasting configurations that just end up with it as a bucket of links to things, etc., etc. So I won't go into them all to save time. So what's stopping us doing all this links? Well, as my colleague Nigel put it, there are 5 main challenges. The first one is about legacy systems and proprietary databases. So a lot of engineering data is in legacy applications. These are often not set up to act as servers. They are improving and they are opening up, but they're not necessarily acting as servers. And even if you did get in, the data may not be fine-grained enough to be useful. You may just get a whole bucket of stuff that you can't find anything out. And again, if you did get in, you might not understand what you've got. So again, this is all to do with standards and interfacing patterns and things. The next major challenge is cybersecurity. So as soon as you start trying to link something, and you're trying to link something that's outside your organization, you're open to hackers and cyber threats, and CEOs get very, very nervous with justification. So often the first answer you get from the CIO is no. And then you start trying to work out how you actually can get across, what security things can you put in place. But that's certainly a very, very significant challenge. The next one is IP. So if you get some data out there, who owns it, who can see it, who can actually open it and have use of it? Maybe you can see the data, but do you actually have a license to use it? How do you get paid for your data? This is very useful or very important these days in additive manufacturing. For example, if you put up a design up there, anybody could actually put it into their additive manufacturing machine and build this thing, make this thing without paying you anything. So that's a very key concern. If you put the data up there, how do you use it? The 5th one is it's really engineering. Engineering is generally a closed world view, whereas the internet is usually an open world view. So engineers, they need safe, reliable, repeatable answers. So when you ask for some information or to get some data back, you expect to get the same answer every time. But when you look at the internet with something like Google, you ask Google a question, you'll get a different answer every day, every 10 minutes. And so that sort of approach is not suitable. So it needs something that is repeatable when you go for these links. And the other one is engineers are risk averse, again, with justification. So it's important that you don't add risks to the engineering products. So this is very key, again, for about the collaboration aspects and the interface and standards. And the final one, as Nigel put it, is time and tide, or obsolescence. Things change. IT systems die, they go out of date, they cost a lot to maintain. New stuff comes along that you want to use, which is better than the old stuff. Data is moved, changed, deleted, archived, etc. So what happens is the link breaks. So what do you do about that? And other things for change management, it's really important to find out, to know what is linked to me. So most things record what do I link to, and they have links on their pages, but to find out what is linked to me is definitely a challenge. But in order to do change management, you need to find that out in engineering. So there is a very rapid summary of some of the challenges for us to think about for these two workshops. As we said, legacy systems, how do we deal with old data, security, how do we handle property rights of that data, how do we keep the risks low for the engineers, and what do we do about legacy and broken links and things moving. So some thoughts provoking some ideas. So what I want to do is get on to the strategies. So as I said before, I'm going to hand over to Eric, but please put your questions in the chat and we'll see if we can work out how to organize them into a sensible selection. Stop presenting.
Thank you very much, Judith. I didn't realize this, but now I realize it's a challenge. I mean, I will try to convince you, everyone, that despite the challenges, federation is the way to go. But I'll do my best and see if I can succeed. So I will talk about an architecture pattern for federated PLM that we have developed at Saab Aeronautics, and also try to justify why federation is important for us. And for those of you who are not Swedish, you might have to be reminded that Saab is, well, of course, located in Sweden. Saab Aeronautics is located in Linköping. It's a rather old company, quite boring business offices, but we are making very exciting products, like in the 50s, the Draken, the Vegan in the 70s, and in the 90s, the current Gripen. And the life in those days were quite predictable. I mean, we had one customer, Swedish Air Force, one operations approach, I mean, national defense, road basing and everything, one project at a time, and very predictable life. It was Sweden and Saab. So in a way, a rather simple life. But then they changed the rules and created a new game. And for us, it's been the Gripen E, which we are doing in collaboration with Brazil, the Global Eye, an airborne early warning platform, and also our part in the TX trainer together with Boeing. So in this new game, we have multiple parallel projects. International operations is just the way it is. It's no longer just national defense on our own. Exports are important. It's very much about international collaboration, multi-site development and production. The regulations that we have to comply with, they're getting more challenging by the time. And suddenly speed is very important. Speed in product development, speed in making sure that we have proper enabling systems for our engineers, and the future that we are looking towards is very unpredictable. Not in a bad sense at all. It's just that we don't really know what's ahead. We know that we will get very good business opportunities, but with whom and when, that's going to be a challenge. So the question is really, if we look at our systems, I mean, they live for a very long time. They are in continuous development. It's not like we are delivering them and then we're doing a midlife upgrade 15 years later. They're really continuously developed. And essentially, the development system's life is substantially shorter than the life of the systems themselves. So if we just look at Gripen, we have replaced our development systems at least twice up to now. So we really have to make sure that we can evolve our development system capability over time. And when we look upon this, I mean, we need new strategies for really thriving in a new and unpredictable world. And the way we are going is to make sure that we align with international best practice. We try to architect our organization and also development environment for flexibility. Of course, we should optimize the overall capability, but always having the capability to adapt the latest processes, the methodologies and tools. And then most important at all, we should be able to adapt to new collaboration scenarios very quickly and at a very low cost. And at the same time, we should be the ones using the latest methods and be the ones who can inspire our partners how to be efficient in development. But just looking back and seeing what are we good at in our organization? Well, generally speaking, if we look at the system of interest, typically an aircraft for us, and then we have all the enabling systems. And just to be honest, we traditionally we've been very good at architecting the aircraft systems, but not so much on the enabling systems. They just tend to emerge. And we just can't continue like this if we really want to be and attain the level of flexibility we are aspiring to. And just to give an example where we are at the moment, our main PLM system is an old installation of Teamcenter. And then we have a large number of uncoordinated front-end applications. We do communicate via documents. So what might be fine-grained information for the end users is turned into a document once we really go into lifecycle management. And this also means that our end users, they are really not working in the PLM system. They are working in the front ends. So this is not a very efficient setup. We have a somewhat better integration when it comes to connecting Teamcenter to our CAD system, but it's very far from ideal. And if we're looking at what we're having at the moment and what is happening in the PLM world, we're seeing we're going from document management. We left that paradigm a long time ago, and now PLM is really about integrated engineering support for essentially all engineering disciplines. So how can we evolve our capability from the left-hand side to the right-hand side while maintaining a high level of flexibility? So in the coming slides, I will present what we call the Genesis pattern. We call it Genesis because we're really starting over. It might sound a little bit pretentious, but well, we're starting over. So our main observation is that we are having, of course, in order to develop an aircraft, we need a large number of engineering disciplines collaboration. We want to make sure that they collaborate on fine granularity product data. But when we're looking at the processes of each individual disciplines, they are very similar. I mean, you capture requirements, you're doing discipline-oriented design, you realize stuff, you integrate, verify, and validate, and finally you declare conformance to requirements. So essentially what we're doing in each discipline from a process perspective is very similar. The product data is of course quite different. So if we're looking into our main flows or processes, we're doing systems engineering, hardware, mechanical engineering, software engineering. We do, for instance, also integrate a lot with our suppliers. So maybe these are our 4 engineering streams. And essentially, we're performing the same kind of activities from a process perspective. But aircraft are safety critical, so we need to make sure that we maintain traceability. And when we are looking into our processes, traceability between the disciplines appears to be for requirements traceability, the ability to capture the product structure, change management, and also the realization of our system, what comes out in the end. And then, of course, we need to have the capability to archive our products. But what we're really trying to do is to optimize the performance within each engineering discipline. Instead of, as we're doing today, where we tell all engineers to use tools because we need requirements traceability. So today we have a very non-connected, non-ideal flow within each engineering discipline. So maybe we can change it, or we want to change it. So what we want to do is to look for engineering discipline specific development environments. We expect them to support full configuration management, full lifecycle management of the information they are managing. For our standard engineers, we want to minimize application family switching. We want them to be happy and live in their own development environment. By doing this, we also like to, or we also strive towards bringing together project management, configuration management, and the engineers, so they are actually looking at the same data. If we want a federation, then of course we need to accept that we will have redundant capabilities in the federation. The systems engineers, they will have their requirements management tools, and the software engineers will use whatever comes with the software environment. So if we're doing this, we have to ensure that we can maintain traceability between requirements in different environments. Another thing is that we want to make sure that we can replace or exchange an engineering discipline-specific environment without affecting the overall PLM landscape. So we all know that in software engineering, the development is the fastest. So we should be able to take out one software engineering environment and replace it with another one for a particular product. Maybe we should continue using the old one for an existing product. But the ability to switch in and switch out discipline environments is something that we value very highly. But of course, we have to have the ability to maintain traceability. And not just traceability to the latest and greatest version of product data, it really has to be configuration management aware. So it has to support evolving versions and different baselines. And as we can see, we are seeing these capabilities emerge in the engineering discipline environments. For instance, IBM ELM or software engineering environments from different vendors. But we need to make sure that we can integrate. And if this model shall be efficient, we really need plug and play integration. So it has to be standardized. And we have been looking at the OLC standard to make sure that we can adhere to a very low number of integration points, but each of them following capabilities in the OSLC standard. And we are doing this, we're in a project called Helipel, where Eurostep, KTH, and Saab are partners. We are obviously promoting Federated PLM, but specifically the Genesis architecture pattern. We want to get experience in OSLC integration, in interface creation, and also to promote and improve the OSLC interface generation tools. And of course, to demonstrate the power of OSLC. And we have been running this project for about a year. It's 18 months long, and we'll apply for a continuation project. But when it comes to OSLC, we can see that the capabilities in the OSLC specifications, they are capable. They do have configuration management support, but as people in the organizations, we're used to doing versioning, the step approach, and OSLC does things another way. So it's been a steep learning curve. Another thing is that in OSLC there are very many optional properties, and the documentation is not very clear. So again, learning testing has been has consumed a lot of time. When it comes to development aids, there are useful test clients and servers, but most developers use Java. So if you are looking into developing OSLC interfaces, make sure you do use it in Java or implement it in Java. The learning curve has been steep. The first interface, of course, is the hardest. And we have spent a lot of time in setting up connections and maintaining connections in an environment where certificates expires, browser security restrictions, they do change. So this has been challenging, but also this is something that is true as soon as you try to integrate anything in between machines. So this is an area where I believe, as organizations, need to invest more in the future. It's not an OSLC problem. So then we may ask, does OSLC work? And this is just an example from IBM linking or interacting with Polarian. Those interfaces has not been developed by us. We just took them out of the box, set them up, and of the 40 hours it took to set things up, about 39 of them was spent on debugging security settings. But what we'll show here is that you can link an existing requirements in Polarian to a defect in IBM, and also to create a new requirement in Polarian from IBM. So let's start. So here we can see the user is in the IBM tool, wants to add a requirement, a link to an existing requirement, goes to the right project. And now we're seeing the delegated UI of Polarian. So we can navigate Polarian from within the IBM tool. We can look at different properties and select the ones we are interested in. You can see also by the selection, it's actually updates things, and the requirement is selected, and we have the link created. We can also look into Polarian, and then we can add the link and create a new requirement. Go to the same project within Polarian, going directly to creating a requirement. We name it. We can add the properties, as you can see below. And then finally create the requirement. We can see that the link is implemented. You'll get feedback as part of the OSLC integration. And we can also move to Polarian and look at the product information there. So this is actually quite impressive, I should say. So just to conclude, from our perspective, we need to prepare for an uncertain future or unpredictable future, but it's an opportunity, not a threat. In order to do this, we need to optimize towards flexibility, so we can adopt the latest support systems, the latest development systems at a very low cost. It's not going to be one system for all products. Whenever we start new product development, we need to select what is the best solution for ourselves, but also perhaps in the partnerships we are in. So what we want to do with this Genesis architecture pattern is to optimize process performance, embrace heterogeneity, And also by doing this, we want to minimize the number of integration points between disciplines. And this is to enable so that we can switch in and switch out applications at a very low cost. And in order for this to work, we need support from standards. It might be OSLC or any other equivalent standard, but plug and play integration is essential. And we're experimenting with this within the Helipel project. And Helipel, of course, is the organizer of this workshop. So we are very grateful for Vinnova, a Swedish funding agency, for supporting us for doing this. So this is why we are interested in federated PLM, and this is the solution pattern we are looking for. And I would like to just provide some questions for you to think about until we meet on Monday. First of all, are there any alternative or better federation patterns? Linking based or information transfer based? A very important thing is also how can we maintain the federation over time? How can we replace a tool and migrate information? From your perspective, do you want to do a proprietary or standards-based federation? Another important thing is, can we set up and acquire supplier integration using this pattern? So we can, as a acquirer, open up our part of our system so the supplier can see relevant information and link. Another important thing from our perspective is that if we go down this road, can we promote new market entrants, the new innovative companies, and give them an opportunity to fit in the landscape of a very large organization? Because we are not expecting them to support everything, just a few engineering disciplines, or just, it's not just, but the activity is supported by a single engineering discipline. Then, of course, we want to influence our suppliers. We want them to provide OSLC out of the box. How can we support them? How can we pressure them to open up for open standards? And of course, the overall question of the workshop, is federated PLM viable to a centralized single vendor solution? So these topics is something I would like you to think about until we meet on Monday for more discussions. Thank you very much.
Thank you, Eric. We shall move on to the second presentation by David. David, are you able to share your presentation?
Let's have a look and see. Share.
I think you can just take over.
Okay, good. Let's see if I can do it from the Windows system.
So there aren't any questions. You keep going, David, and we'll see. Does anybody have any questions while we're there for Eric? There aren't any in the chat. If you have any questions, do you want to raise a hand? And before while David's getting sorted.
Sort of, he's offering me too many alternatives.
Michael?
Okay, good.
Yes, thank you. I didn't see, Eric, in your slide something where you have this, if there is a need of having control or getting control or getting information on the, so to say, totality of the federated systems. Is that something that you have been looking into as well? That if you want to this DNS thing similar, where you look up where all the information resides, or the, as I say, connected systems, if that is something that you have looked into as well, the top level architecture kind of thing, so to say.
So for us, I mean, we don't, the product data we have generally belong to one aircraft. So the entry point is the top level of the aircraft, and then of course you can navigate and search within the individual environments. But I think in this particular case, our business situation is a little bit different compared to the one you are facing within Ericsson.
Yeah.
But we might need that capability.
Yeah, because that is some concerns that has been raised within our company. Then, as for example, Mats and myself are supportive of a federated landscape, but then there are in some cases a need of getting the complete picture for some reasons. So it might be a capability that needs to be looked into in your as a complement to your very good slides.
Yeah, and what we intend is, of course, I mean, by having the links, we're also having the capability to traverse the product data. So it's not that things will be isolated.
Yeah.
But again, it will be based per product, and we generally speaking we have few.
Yep. Thank you.
Thank you.
Any other questions before we move on? No. Over to you then, David. You need to unmute. We can't hear you.
Right, now you can hear me.
Now I can hear.
That's good. Okay. So yes, this is going to be a slightly different perspective, and I'm presenting on behalf of myself, David Cameron, who's the University of Oslo, where I work in something called a Serious Centre for Scalable Data Access in the Oil and Gas domain, and my colleague, Professor Martin Gieser, who will be representing us in person. There's Martin waving there. He'll be representing us in person at Gothenburg. I am unfortunately teaching on Monday, and since my boss is running a course, I can't really get out of it. So what I'd like to do here is describe a work about trying to integrate the standards in the chemical processing and oil and gas industry around bringing some system engineering and product lifecycle management perspectives into what we do in engineering, procurement, and construction. So, and I'd like to start with that there is a definite difference in emphasis and role of PLM in the engineering, procurement, and construction industry and the manufacturing industries. We see also that things like Industry 4.0 is driving some sort of convergence in that a lot of EPC companies are now making reproducible product lines, like a certain family of HVDC transformer platforms and things like that. But there is a difference, and we see this very often when we discuss these sort of issues about interoperability and system design. There is definite difference in focus and responsibility between chemical engineers like myself and mechanical or aeronautical engineers who are looking at making specific products. And we'll come back a little bit later to what does a product mean. Now, the context of what I'm talking about is a project which has been run on the Norwegian continental shelf, where engineering companies and operating companies have deliberately tried to emphasize that they're going to try to use digital methods and digitalization of requirements and digitalization of asset models to demonstrate how they can exchange data without using documents in a field development process. And that field is a field called the North of Alfheim, Krafler or Usher field development. And it is actually, as you see, an interlinked development with 3 platforms and lots of underground production subsurface underwater production facilities interacting together. People are on that platform, everything else is unmanned. Lots of services for this platform, which I've been looking at very much in my modelling work, which is called Krafler, will be supplied by this platform, which is where the people and most of the services are. And it's very important because of the strong interlinking of the different facilities that there is exchange of information and that information can be exchanged in an interoperable way. And what we see along a construction of any large capital facility, like an oil platform, is that as you go through the stage gate processes, every time you hand over to make a decision, you create lots of documents, you then forget what has happened behind that, you forget the requirements that have gone into that, and you have a constant loss of knowledge about your plant and how it works. And what I guess the ambition we want to do is we want to build a digital twin of what we're building during design so we can use it in operations. Now, digital twins is an incredibly complex and buzzword-laden area, and everybody seems to want to make a model of digital twins with as many boxes and a 3-dimensional thingamywatties that they possibly can. I'd like to break that down into that if you're going to build a digital twin as an application to try to do something, you've got a very simple conceptual model. You've got some system that you want to make good decisions about. And there's users with lots of different roles and interests who don't want to be distracted by irrelevant information. And your digital twin needs to combine 3 things: the system's design and configuration, simulation and analysis based on that, and the measurements and observations that you have of that system. Now, what you need to do is to fuse all that information together and then do some sort of analysis, reasoning, or decision support so that your users are capable of operating your oil platform or oil field in the best way, or your pilot can fly his or her plane, without crashing it. Now, when I talk to people in the aerospace industry, they have a very, very well-defined tool set where system engineering is pretty well embedded into it. What we have in the oil and gas industry and chemicals industry is a very specialized and legacy toolkit, where the tools were often built by chemical engineers who knew a bit of programming. And so what we have at the layer of bottom is a set of databases which contain design information. Then on top of that and supporting it, you have a set of 3-dimensional modeling and CAD tools. And there are 3 market-leading products there, but I could list up others. And then the simulation is done by specialized simulation tools for the oil and gas and process industries. And this is probably the most complicated diagram I say, is that a digital twin is something that needs to live inside a digital system model. And that digital system model at the moment is spread over all those databases and simulators that I showed you before. And we need to be able to carry things through this system model. Okay, so that's what I'm going to say about digital twins. Now, the petroleum and process industries have worked for decades in describing engineering data and trying to enable digital twins. You know, the ISO has these standards, 10303, which is a very manufacturing standard, and 15926, which was branched out of that for the sort of reasons I was talking about being the differences between EPC and manufacturing. Lately, there's been a lot of work around a systems designation standard called 81346. Then there's a whole stack of other standards that are relevant to this sort of work. In Norway, the oil and gas industry got together in a so-called joint energy project to try to work how they could digitize requirements one step better than what we have in Polarion, to try to make the statements not just text statements cut out and put into a database, but to turn those requirements into something that is actually calculatable and machine processable. That project discovered very early that to do that, you actually needed a good and unambiguous way to point to some place where that requirement should be applied. And so they took a right turn and started working on an information modeling framework so that you could provide a place for requirements to refer to, and so that you could actually trace requirements down through the design process. Now, around the oil and gas and chemicals industry, there's also a large number of industry-specific groups who are doing work around trying to provide reference data or data models that will enable federation of data and handing things across. Things like the IOGP, which has the CHIFOS initiative for handover data for capital facilities. The German chemical industry has the DEXB standard, and also Namur and various other things coming out of the German industry. Now, what we're trying to do here is integrate the best of these things to provide something that would actually be demonstrably usable on the NOACA field development. And we still have constant problems. This is from 2011 on why federation isn't working in the industry and why asset information standards aren't used. Things like complexity of the architecture, ontological problems hindering use of the standards, complexity of implementation, resistance to change. These issues are still completely relevant to 11, 12 years later. And we have quite a lot of dots to join. I won't waste your time on that, but these are things and initiatives that are going on in the industry that need to be tied together. And finally, we have a challenge with what I would call weasel words. Words that we use and we think we know the meaning of, but when we talk to somebody in another community, we discover that no, it's not what we're talking about. So, for example, product has one meaning in manufacturing and then a completely different meaning in the EPC industry. Your product is the thing, your product is the thing you make, and you as a pump manufacturer supplying to us create a product which we buy and then put into our plant, which makes our product, which is chemicals or oil. Function is a difficult word. Process is a very difficult word because chemical engineers building the design of a facility are talking about processes and process steps the whole way. But then people put their hand up and say, oh, but we've got the design process, the engineering process, the maintenance process. So that's a complicated word. Streams, systems, activities, functional objects, locations, functional locations, and tags are all words which need to be very carefully defined when we go into dialogue with each other about these things. And I think the story I want to give you today is, at least in the EPC industry, we have okay models for representing the installed equipment and what you actually build with some sort of tag structure. We're good at modeling actual bits of kit. ISO 15926 and CHIFOS and DEXB standards to do that. But what we lack is models that allow us to do systems thinking, top-down design, and what we'll call aspect-oriented design and digital twins. I'll just go in and try to explain a little bit. So bear with about 2 or 3 minutes of philosophy. People have reference data and people like building knowledge models. And there's this term of ontology, which is about trying to classify the things I have. Now, there's actually a big philosophical debate about, well, what is a system ontologically? Is a system a very big physical thing consisting of lots and lots of parts? Or is a system some sort of conceptual object that you try to visualize reality. Now, if you go to the standards, 15926 and I think 10303 is pretty clear that systems are assemblies of functional objects, and functional objects are physical. 1596 part 14 says it's a complex of functional parts, but again, those functional parts are physical objects. Fortunately, there's an alternative way of looking at it as a system of being a way of analysing reality or analysing the reality you want to create. And so 81346 part 1 says that it's about an interrelated objects considered in a defined context and can be conceptual or physical. And INCOSE also has a good definition about that, which is saying that there are both conceptual and physical systems. Now, when we come to trying to do interoperability and federation with the current standards we have in industry, we have a challenge because they all take this first approach of that a system is just an assembly of physical things, or that a system which does something, a functional system, is just a big, a pumping system is just a big pump. Now, what I'll show here is that no, that's not the case. A pumping system is a pump together with all the other bits of equipment that you need to actually ensure that that pump will run successfully, safely, operably, and do what it's intended to do. So what we've developed is an information modelling framework, and this is being delivered by this joint industry project. And it's based on the 81346 standard series, in which we do good systems engineering. We create complex systems into subsystems, but we do it along what are called aspect trees. Now, you can type or designate these systems using a reference designation system. We've developed one for oil and gas, which is easily extendable to the process and energy industries. So that gives us a type of systems that we're actually building our knowledge model of. Now, what it does is it separates function from the physical object and its installed objects. And so this gives us better places to put on high-level requirements where they should be up in the structure, instead of trying to find a place down in a very detailed data structure related to what's actually installed in the plant, where you put requirements, and it allows easier abstraction. Now, it integrates the old tag-based and product-based approach in this product aspect, but it doesn't lock us into the old approach. So it's built on ISO IC 81346, and if you're talking about industrial tagging, you've got a tag on a pump, and you then talk about the function of a pump, you talk about the location of a pump, and you talk about the actual physical attributes of a pump, its weight, its impeller size, its dimensions. Now, 81346 says, talk about those aspects using separate objects. Talk about the functional objects using a functional system description. Then you can talk about the things which are inherent in the actual piece of equipment using what they call product aspect. It's a difficult term in our context. We'd like to talk about components or equipment, perhaps. And then you can also say, well, I'll also have an object which says, where am I? And then you can create further aspects. So you could have an object which represents the actual installed object, or you could have an object that represents the commissioning information about the object, or you can have an object that represents the maintenance information about the object. And so what we see for us is that you can have a federated system, and this is actually an old diagram taken from about a 10, 15-year-old paper. But what we say is we have a single system we're looking at, very, very complicated, can be conceptual, can be physical system, which needs to fill up requirements. And we actually build 3 trees of objects to organize our data. The first thing we do is we try to model a process using functional blocks. Then we model a plant using product blocks, which resemble the blocks we have in GFOS and DXP. And then we can also then put in objects that represent the actual installed equipment digitally. so that you have this mapping across and tracing of a functional representation and a physical representation. And what this enables us, if we're trying to make decisions in practice, is that during conceptual design, you actually start top down with very high level requirements, and you build a more and more detailed functional model of what you actually want to do, the process. And interestingly, once you're in operations, most of the optimization and process behavior things and process troubleshooting that you'll want to do is not so much about how the equipment behaves, it's actually about, is the process doing what I want the process to do? And so it'll be very useful to be able to capture the requirements that you put onto these objects when you're trying to do zero defect operations, when you're trying to optimize performance of the system. But during design, as you go down the V, you get to a point where you're saying, okay, we now know what we want to do. We now apply equipment requirements and constraints to actually specify the equipment that will do these activities. And so we flip aspect into this product aspect and start building up a model of blocks down, which gives you the basis for doing your maintenance. Because there you've got what the equipment's supposed to do of itself and things which are related to actual behavior of the physical equipment. And so you monitor there things that you need to do maintenance. So does the equipment meet the requirements? And then further up, does the process meet its requirements? And so here's a further view of it, saying that you can use this to support both operations and maintenance and the sort of things that you'd be looking at each of these layers of the system. Now, what we see is this fits in a situation where you have corporate systems that already exist there. And so this asset model is a way of referring to and indexing things that we're going to have in other places. And we also don't believe that it will be a semantic model, but we do believe that the blocks you use to build the asset information model will be typed by a reference definition and language, and will also be linked up to an ontology or a semantic model so that you can do reasoning and validation around what you're actually building in an assets model. So here's a simple example about how we separate function from equipment. You build process design by saying what you want to do. And we notice that these blocks are typed by activities, things you want to do, like cooling, pumping, driving, distributing. And you build that model down, and then you say, okay, that pumping function needs to be fulfilled by an object, an artifact, that is a pump. Oh, great, okay, good. But you then have this ability to link requirements that you put here on the function to requirements that are then placed on the actual piece of equipment. And then you can also say that that pump will live in a pump enclosure. So you can also build up a model of the location of your items. But what we have is separate objects, which can be linked together in very rich ways. Now, we're not alone in thinking about this. The NPRO project in Germany, sponsored by the German chemical industry, sees this as well. But functional requirements give you a process structure, and that process structure is defined by activities. You then go into a functional design where you start to move, you're still thinking function here, but you're now thinking about function of physical artifacts. And then you're making a plant specification, and that's very much about saying, what pieces of equipment will I buy and install? And once you're in operation, you're very much concerned about the actual equipment in place, but we still want to have that traceability back to functional requirements. So the sort of data you have in a heat exchanger is either functional aspect, yellow, or product aspect. And what you see is that certain documents are very, very related to functional requirements, like the process flow diagram, whereas your piping and instrumentation diagram is based very much around what pieces of physical equipment I'm going to have there. So We structure our model in IMF in the same way as you would actually in XML, that you have blocks which have ports which present interfaces, and then we can say that an interface, a port, can either transmit material, energy, or information, and the structures, the information defined by that is defined by a template. And so our working practice during design is we start thinking about function. When there's no thought of what the plant is, we start saying, what elements do we need at very high level to get the oil and gas out of this field and sent off to land? And so we start building a field block diagram, and then we define what sort of technical systems, high level things we have to do to process the oil and gas. And that then builds down in a very tree-like structure to say, well, okay, and then to do this, we need to actually have these low-level component systems which still do functions. And then we need to put on supporting functionality to make sure that these low-level systems behave properly and are safe and can be relieved and can be drained and can be maintained. I'll come back with some examples of that before I go on. And then you say, okay, at some point we can hop over and say, well, we actually need some equipment to do that. And so you can start modeling it using blocks in what's called a product aspect, where you have a block corresponding to each piece of equipment, each physical object that you'll have in the system you're trying to build. And they can then be mapped to installed plant items so that you are able to create a digital twin and also an inventory of what you actually have installed. But you have separate objects so that when you replace something, you replace the installed plant item, but you still got traceability back to the specification of that plant item in the product aspect. We're also very much involved in DEXB. So DEXB has a nice standard for representing information on piping instrumentation diagrams. And they correspond to our objects in the product aspect. What we find is that demonstration PIDs are a bit too simple, and we need to do some work about this. But what we are trying to do in the NOACA project is to demonstrate that you can use DEXB to send PIDs between engineering companies and operators in a successful way. And it's working pretty well. You know, there's a lot of finding bugs and coming back with features, but the method has been proven to be able to work very well. But that's for equipment, because you've got every object on a P&ID is a piece of kit, a piece of equipment. DEXB Plus is about modeling process flow diagrams and process block diagrams. And that's functional modeling. And so that's the same sort of thing as we've been doing with our IMF modeling. And so we're working very closely with DEXB Plus to be able to have interoperability between these two ways of representing it. And it's going to be basically just about terminology, whether you have a DEXB Plus model. And I'd hope that we can get a convergence between our modeling approach with DEXB Plus as a standard for how we describe chemical processes. And then we type these blocks using activities from the 1596 Part 14 class, so we have a nice rigorous semantic model that we can use to reason around these models. So this example then becomes, using DEXB Plus blocks, a data model that can then also be used to organize the design data further down in that system. And so this is an example which will be published as soon as the DEXB Plus report is finished in about a month, which shows how we take this standard PFD and model it using a candidate set of standard process functions to represent what's happening there. Chiefos has a data model defined with its own reference data. What they don't do is that they don't separate out functionality, the process model from the equipment. And so they have a much too tight linkage between what a process is doing and an actual single piece of equipment. DEXB Plus explicitly doesn't have that, and IMF doesn't have that as well. So what we also then have is a resource that you can use and review is that there's a reference designation system that gives us a way of labeling objects in the model. And you can get that spreadsheet from the Ready project website. And Equinor has noted that SysML tools are something that process engineers and a lot of discipline engineers and EPC companies are allergic to. So they're trying to build a tool for system modeling using this approach that can be used by mere mortals. That is an open source project, which you're welcome to contributions, and we'd like the source of that is there. And I'd like to finish off for about 5 minutes, 10 minutes, to talk through an example we've just published, which shows this approach and demonstrates it and has resources that you can go and have a look at. So the chemical industry has always had a problem that academics have had problems getting access to non-trivial examples. And so about 20, 30 years ago, Tennessee Eastman Chemicals took a real process and did enough information to anonymize it to provide a test case for people who wanted to do things around control system design and things. And so this is a spreadsheet, so this is a flow sheet where you have 3 chemicals coming in, you have a reaction which produces a lot of heat, so you have to cool it, and then you have to condense the gas which comes over the top, and then you've got to separate out the product you want from the things which you don't want around the system. You have to recycle a lot of material, which means you need a compressor, and you need a separation tower to create a sufficiently pure product of what you want to make. So the papers, this example's got about 40, 50 academic papers which use it as an example. So I used it as an example to demonstrate how we can use IMF to model functional work. You can get the paper, you can get the website to have a look at the model, and you can get an Enterprise Architect model file or XMI from these links. You're welcome to go use them. So we start off with the model and say, hi, we want to do some chemical processing. And so we create a top level block, which is a processing system. And then we go down and say, well, what do we want to do? Well, we need to do some reaction. We need to do some heating exchanging. We need to do some separating. We need a cooling water supply system. We need a steam supply system. We need to do some separating, and we need to do some compressing. And these things correspond to process block diagram for the process. And it's vanilla SysML as well. And we then create subsystem, and we can generate a flow topology. So we can drill down and say that, well, a thermal exchange system consists at a lower level of a certain type of heat exchange system. And then we want to do some monitoring. We need to control the flow out of the system. And so you actually get the level of detail where you can actually start creating a flow topology of the plant. Now, this model at this point is deliberately not able to be built or operated. We need to add additional functionality, control, safety, support, and then we actually have to realize all those functions by going out and buying and specifying equipment. So we go in and say control, well, we actually have to have control temperature and phase of the product out, and we have to limit the cooling water return temperature from the cooling water of this heat exchanger. And so that means that we can postulate that we need a control function, we need a monitoring function, and we've got a place where we can actually control the water flow rate. So we actually have this water control function. Now we're all still just thinking about things we have to do. Then you have to think about safety, that you have to put in addition things to say that I'll relieve the system and keep it safe. And they're all required from standards like API RP14C, which says if you've got a heat exchanger, you have to have a relief valve here unless. You have to have a relief valve here unless. You have to monitor pressure, you have to monitor temperature. And so we say, okay, good, we have to put on some pressure relieving function. We have to monitor temperature, we have to monitor pressure at these places. And so there are additional functions which will again be realized by needing to buy some equipment. And then you can start saying, well, I actually want to buy pipes and heat exchangers and valves and physical things. And I need, in addition, to be able to monitor the condition of it, I need to be able to vent, I need to be able to isolate or drain. And each of these things I again need to do. Now, what that means is that if you're trying to think about that a separation system is just a big separator, you've lost all this ability to connect in requirements at a level, and you've lost the ability to actually be able to say for a specific piece of equipment in your plant what its function is. So this way of modelling has enabled us to create something which we call a functional P&ID, where we say that a separation system is not a big separator. It is just a separator with all these 25, 26 additional things you need to do to the separator and with the separator. A lot of them about monitoring and sensing, but other things like jetting to make sure it doesn't clog up with sand, or putting a manhole on it so you can actually do some maintenance. But each of these things are capable of explaining why you have a specific piece of equipment or a specific assembly on your actual P&ID. And once we do that, we can talk about equipment. And so what we see here is that we build our functional model, which is recording all the things all the information we need to know about the process, what we're trying to do in the facility. And then you realize it with an equipment assembly, which you can then fill up with the artifacts that you need to actually buy, the pipes, the valves, the actual heat exchanger itself, further pipes, further valves, a relief device. And what we see here is that those blocks can be drawn from Dexby Plus, and they're typed by activities. I want to do heat exchanging. Whereas these blocks are from either Chiefos or 1596 Part 4 or Dexby, and they're types of physical object or artifact. And these things have tags. These things at present inherit some sort of vague tag from the equipment, the main bit of equipment in it. So what we've done in this model is we've provided a very unambiguous way to put your functional requirements at the right level of a design so that you can get them back later. So this is what we've done. We've taken about 5% of model-based system engineering and used it as a way to organize the information of our engineering in a way which engineers understand and engineers will appreciate and engineers actually do implicitly at the moment, in a way that we believe will allow us to achieve a much greater traceability of the requirements that we have in the engineering process. So sorry that it was rather fast and probably a lot of material, but I'm looking forward to sending my good colleague, Professor Gieser, down to explain it in more detail on Monday.
Thank you, David. There's been a few questions going on in the chat with a few answers about software, but Michael's, Michael, you have your hand up. Do you want to ask a question?
Yeah, based on David's last slides here, the functional aspects and also then the equipment part, would you see that as going on in the chat as well, that an application going forward will be treated as an equipment as well, as the top level will be more the so to say virtual thing, the software part that is running on top of an hardware installation? Is that something that you will cover as in your slide that talk about equipment, and then it's both hardware and software.
Oh, we're going to have to talk to the automation people about that, because I've seen some ambiguities about what the role of a software or control algorithm is, because we talk very often and very easily about functional modeling in automation, in a way which perhaps we should try to abstract up a little bit about this, because the chemical engineer meets the automation people with a statement which is expressed in or meets the software people, let's say, with a statement which is expressed still in the chemical engineering domain. You know, we've got a model which is going down here where we're saying we need to measure something. Now, that maps pretty closely onto the automation engineer or software engineering. So, okay, we need to create an input here. Now, I would propose that a lot of the things that you show on automation diagrams, like system control diagrams or ladder logic diagrams, are actually much more in the product aspect than they are in the functional object aspect. But what we see in some standards is that you'll be having a P&ID, and then they'll put a controller on, and they'll tag out as being functional rather than actually being a physical, in inverted commas, controller.
Yeah, no, I agree with that, and that's why we bring it up as an equipment has both the functional aspect, but you have also the product aspects, and then the product being either a hardware or a software part, as the software part can be on top, as
exactly, yeah.
For example, in our industry, we have a lot of software defined functionality in the radios and basebands and so forth. And then the system becomes more and more complex with not only physical things that you stated in your early part slides in the presentation. It's more than just a physical thing. It's an integrated part of any kind, more or less.
Yeah, I would. Yeah, that means I think we need to talk further around that linkage between in our domain, linkage between the equipment and the automation, which is where the software comes in with us, and find out and do a bit of thinking about which bits of the software are thought of analogously as components or artifacts, and how you can abstract that functionality up into higher level functional things.
Yep.
And that is going to be a very interesting challenge, because there's a lot of weird things being said about what is the ontological status of software stuff. And so we just have to decide, okay, good, a piece of software is a man-made thing, and it's got an interface.
Yeah, for your information, I have personally had some contact with Erland on this, how to bridge the telecom with the processing industry in this context.
Yeah, interesting.
Thank you. Johan has his hand up.
Yes. One way of thinking about this 81346, I've been using it for about 15 years. If you look at the product structure as an assembly structure, that is how you put the things together. That is, of course, important. That's the MBOM for PLM systems. But if you think about the functional aspect, you can divide that in further details. So if you take a brake systems for a car, or braking systems, you can have the sort of main functionality for the brake systems. Perhaps you show that on a P&ID or other functional main description. Then you can have the power functionality which could be hydraulics, air, electrical power. That's a different kind of functionality for the brake system. And then you have the control functionality for the car, for the brake system. And that can be implemented in different ways. In modern car, we usually have a lot of software for the braking capabilities, ABS functionalities, for instance. So it's very good to split up the functional aspects in the main and the power and the control aspect. So then you have the complete braking system that of course must include the software with interfaces to other systems. So that's my way of using it, and it has been used like that in the nuclear power industry for decades. That's very useful.
That's good. This presentation has suffered from the fact that we've only modelled one discipline down a tree. What we're doing in Cruffler is that we're doing precisely that the electrical discipline is modelling down the electrical system tree, and the automation people are modelling down the automation functional modelling. And so the ambition here is that we have here is that we've got blocks in our process function discipline that need to be connected to functional blocks in the electrical or the hydraulic or the safety or the mechanical discipline functional trees that are being developed too. So that's exactly that. And sorry that the presentation has only shown you one discipline tree.
But it's very interesting, so it looks good. I like it a lot.
The other challenge about RDS is that RDS tells you what you've got, but it doesn't give you any handle on what's actually happening inside it. What we've got in IMF is we put parameters onto these classes so you can actually refer to numbers and refer to commonly agreed parameterizations.
Michael, you still have your hand up. Did you want to ask another question?
No, sorry, I forgot to raise it on.
Okay. So I have a question. It's just trying to link the two presentations. You just mentioned there about linking the different models together. You talked about you had a functional one and you want to link to safety and whatever else. Have you any sort of thoughts on how you do that without copy paste? Or have you come across come to that problem and actually how do you solve it?
You don't copy paste. What you do is that you maintain the different discipline models, and then you can either connect by saying, oh, that port there actually is fulfilled by a dangling port in the functional model in the automation domain, or in the safety domain, or in the electrical domain, and so your models actually get together. Or you can also use trace relationships. And so you can build parallel models, but the joy of the whole idea of this sort of 81346 is you can say, I want to create a relationship between these two diverse models.
Right.
And these models should be fairly thin. We want to be able to use these models to define structure. Please don't put numbers into them, because the numbers, what we want to do is this provides a way of unambiguously saying what the number is and how it's related to something. But as soon as you start putting numbers into the actual model, you're in a situation where that model has to be duplicated or copied. This should be a way of referring into numbers you've got in places which are actually good at storing numbers, like databases.
Right. Okay, so they're sort of, those links are assuming that the models can talk to each other using 81 the standard. Yeah.
Using either a semantic web protocol or the SysML-OLDC protocol.
Okay, thank you. Eric?
Yes. So would it be correct to say that you are integrating the information views in SysML, and then your federation approach is that you are taking information from different sources and join them in the SysML view?
Yes, basically. And what we also see is that what we want to do is the existing data models we have for asset information are very, very equipment oriented. And so what happens is that you go into something like Kermos or Zycad and say, what information do I want about a distillation column? And you go in and say, well, okay, a distillation column is a distillation column, equipment, and it's got 650 parameters. And they're sort of vaguely sorted by, are they relevant to the actual construction of a thing, or are they related to the process? Are they related to the process function, or are they related to the materials? And so what we're trying to do here is also providing a rigorous way of making sure that you know about the information and can keep the information at the earliest possible stage in your design, so that you don't have to do the troubleshooting analysis of going down and crawling through these 650 irrelevant parameters to find the information you need to use for process optimization.
So can I ask a follow-on question, which I'm just trying to formulate it in my head? In my domain, every new aircraft is fundamentally different compared to its predecessor. I mean, the architecture change. Would you say that you have kind of a mature architecture that you just optimize over each product generation?
No, historically, every platform is custom, is tailor-made for its application. So we've never really had product lines.
Okay.
We're moving towards product lines now as people are moving into renewables, where you say that we want to have achieved much more reuse of designs and evolution. What we do have, however, is we custom build from pretty well-defined building blocks.
Yeah. And those are known since, I mean, a long time ago.
1910. Yeah, Arthur D. Little invented the concept of chemical unit operations, what, in about 1896 or something like that.
Thanks.
Any more questions? We have time if anyone has any more questions.
Can I just make an observation also? There's actually a very interesting area of meeting here between the manufacturing sector and the EPC sector. Because when we get down to the bottom level of our modeling, we're actually making an interaction point towards what's coming out of your PLMs. So, you know, we specify that we need a gas turbine. The things we specify have a meeting point and an interoperability point with what you're trying to publish out of your PLM and what is the end result of all your product functional and product modeling.
Johan, you have
Absolutely
your
true.
hand raised?
Yes, I have a question. How are we thinking about Monday and the coming days? Are we focusing on systems or system of systems where SysML could be used as modeling, or are we thinking about enterprises as well, where unified architecture framework or Archimate can be used? When you have a plant, a power plant, then the enterprise and the system is quite closely connected. But when you have production for automobiles or airplanes or submarine, as I have, then you have sort of the products is a smaller part. Then you have the whole enterprise as well. So do you think we are we going to talk about enterprise level as well?
Eric, do you want to answer that one, or shall I?
I can make a try, and because I think the focus of all our discussions should be about federations, whether they are feasible, whether they are required, and how we can create efficient and intelligent federations supporting different use cases, be it in oil and gas or in production industry. And those federations may, of course, also include enterprise level concerns. That would be my try to answer it. What's your view, Judith?
So I was coming back to, let me just share the sort of summary slide that we have. Let me just find the right page. Yeah, so we had the 4 topics for federation. I'm just working on it. Sorry, this one. Let's just see if I get the right thing. Yeah, so we had the 4 topics. We've talked a lot, I think, about federation, the different strategies from Eric and David, and a lot about standards and things. So those are the two of the major topics that we wanted to cover. The other 2 are about how you manage the life cycle of things, whether it's a digital twin to a real world system, a real world thing, or whether it's a functional to a physical, or those sort of things, and these change over time, and how do you manage it? That's one of the topics we were going to try and brainstorm. Another one is the collaboration aspects of different you could be talking about organizations, across teams, IP, those sort of aspects. So that's the sort of areas that we were planning to focus on, or how discussions around those headings.
Okay, good. I think item number 4 is a lot about enterprise and collaboration.
Yes.
Yeah.
Well,
yeah.
That'll be interesting, because we have an enterprise and collaboration constellation, which is, it's not quite as complicated as the A380, but we've got the equipment suppliers, 2 EPCs and 2 oil companies building stuff that has to talk to each other. So it'd be interesting to see a little bit about how we can see that aspect.
Yeah. Okay. Again, I'm looking at time. Any more questions before I sort of get on to the planning for next week? I've lost my screen, so I can't see raised hands. Oh, yeah.
Bjorn's got his hand up.
That's good. Torbjörn.
I just wanted to ask both Eric and David. First, David, when you are moving on with this, do you think you will run into the same topics that Eric is presenting, to set up a system landscape supporting plug and play and so on? Right now you're on a more abstract level, as I understand it. Or how do you see the implementation of this in large scale in oil and gas worldwide?
Yeah, I think we're going to I think you agree that we are going to run into those implementation issues and the software suppliers are going to have to provide interfaces so that you can interact with it in this way. So that's why we're trying to standardize up through GFOS and DXP, so that we have the chemicals industries with us as drivers for this. And we're trying very, very hard to try to integrate standards and build up something that it'll be easy for software vendors to do, because it's actually well defined, well integrated, and lightweight, and can sit on top of their systems, making sense of it.
Because I think what we are doing with OSLC and the Helper project is that we set up this kind of ecosystem with many players and many systems, and we know how we can talk to them, and you publish your capabilities and so on. And that would be very interesting from my point of view to see what you think about that when you have a more open, standard-based approach to the information, if that will impact the way you do it. Because what we do with OSLC, we don't bother how the different domains structure their data, while you are doing that very much, I think. Or is that a misunderstanding?
It's a bit unfair. Our biggest challenge at the moment is that I'm a novice in SysML, and it was very, very good for developing a very, very complicated model very quickly. And it was very, very good that the IMF modeling concepts and SysML basically fell on top of each other. My biggest challenge now is to get the information, the amount of information we actually have in the SysML that is really interesting for us is very, very limited. And it's currently packed into ginormous XML files, which are full of graphical representation. So to have OSLC as a way of getting the information which is actually relevant out of a SysML model in a way that allows it to be interoperable is my biggest need just now.
Okay.
Yeah.
And same question to Eric, really, with all your thinking about the Genesis pattern. Do you see that there are things that been going on in oil and gas that we will have benefits from in Genesis, or are we giving away all responsibility to the vendors how they do things internally?
No, I think there is an extremely high value in the approach where you can take reference data and just extract it. You can agree on the product properties, as I think you are doing very well. It's an area where I say we are quite weak in aerospace. We don't have the generally agreed set of properties we capture for individual products. It's all on a case-by-case basis.
I think we need to look into this in the next step of Helper. But
yes, absolutely.
Yes.
Yeah.
Okay, thank you.
Mats, you have a question?
Maybe just an observation here from my end, basically, is that what we saw in OSL, what I've seen of OSLC is not that much, but basically we have the requirements process that is fairly established, and the change management process is also fairly established, but there are other process use cases that are not established and hasn't happened in OSLC, even if the technology is available. So it would be interesting to see also why it didn't take off, why didn't semantic web take off in the sense it did, and what is the stopping if you want to go on this, because our challenge is I would like to do more sort of the traditional design product federation, even internally based on some standards, not necessarily being let down to software package vendors, data model discretion, basically, but use something in between and use mechanics and, as you say, be able to get long-lived links, so I don't tightly integrate like a door system and a 3DX system or something that is totally glued together based on their internal IDs. So you need to have some kind of mechanisms to have this in a maintainable way, because we say plug and play. Maybe I want to swap out an environment in the future and say in 5 years I find a better tool for doing something, even if in your case, Eric, on the same aircraft model, I want to swap my environment for a better tool I have. And if you then hard glued all the links of something, it will be almost impossible to do that operation. And kind of have this on one side, and then you have what you presented, David, which is more sort of the ontology and the higher level abstract modeling, how you represent your both processes and the assets involved in a plant, and see how can we bridge this. I mean, I think Micke Hjalmarsson talked about it here also, like in our telecom industry, it's not that different from a chemical plant. It's more like that there are other owners of the assets, because we sell the assets to an operator or somebody who is operating this. But really, nowadays, you would like to have digital feedback coming back, and then it's more like a commercial, practical amount of saying what data feeds do you want, but you want the feedback to come, basically. And you want to be able to do some of this stuff, figuring out basically how can I bridge the tool set into something that I can plug and play. We're still a little bit fascinated by the fact that I can get a delegated UI pop up without logging in more than 2 times basically, and some security hurdles. But there's quite some way if you want to do this one. And also, as someone said here, can you apply analytics, or can you apply other data extraction techniques on these links basically to have a better understanding of the universe of federated links? I think IBM has something, but I think it's not mature enough yet. But it's another aspect of the enterprise indexing, or whatever you can see it to.
How do you do data mining and AI and stuff on
On top
data?
of that, basically,
Yeah,
when you're
very
bound by
interesting.
proprietary systems and depending on licenses and whatnot, and you have to honor data security and who can get access to what, because you still want to be able to give designers and other engineers and anybody who is interested in this see their slice of information that they will benefit from, but only that information. It's a huge and very interesting field that you're describing from both spectrums, basically. So I'm very excited about that.
And it's, I think we have to start someplace, but still there's a long way to go.
Yeah. But has anybody reflected on why it didn't happen as it was promised in the mid-2000s, basically, Web 2.0, semantic web, everything, this RDF and these things is nothing new. It has been around for a decade, basically, or more. But why it didn't happen?
Rubbish tool support, I think.
Yeah.
Martin could say, yeah.
Oh,
or is it like as simple as it has different points of view from the tools vendors that nobody's really interested in doing open, even if they have to say so?
I mean, it's a long story, but the thing is that the whole idea was hyped quite a lot back when you were saying, but the research has been lagging behind that to actually make it possible. But that doesn't mean it's not possible. It means that it wasn't possible as quickly as the hype tended to suggest, which put the whole area into discredit. But the things that we can do now technologically are far beyond what we could do 10 years ago. So that is one aspect, of course. But there are very many other aspects. I mean, one is the idea of saying now we're going to do this all semantics. So we're going to model our domain. We're going to model our enterprise completely. We're going to do a proper job now. We're going to model it all, and then you never get out of this modeling pit.
Yeah.
So
you can't do anything, because then you're boiling the ocean when it comes to debating about the modeling, and it's not practical.
Yes, yes, yes. Indeed, indeed. And I mean, in newer projects, we're trying to, rather pick parts of the domain and model those. We're looking at how could you survive with having overlapping but different ontologies for parts of your enterprise and so on.
So like you figure out how to mix your red and greens to get another color that you're interested in that domain and not do everything. Okay, thank you very much.
I could offer my perspective. It's Andrew Berezovsky speaking. I was a co-chair of the OSLC open project for the last 5 years, and I've just stepped down probably a few weeks ago. You asked a lot of questions, so I'm not sure if I'll be able to answer all of them in 10 minutes. So the semantic web, I think it failed because a lot of focus was on human aspect of the web. Some people were thinking that you'd need to annotate every web page with information for machines. I think it's a very wrong reading of Tim Berners-Lee view. I really welcome everyone to watch his 1994 presentation at CERN. It's the first World Wide Web conference. It's a very short and very simple presentation, and he was actually using a slide projector for real OHP film slides. And he was showing how real physical objects have the same representation on the web. And it was 1994. It was like 15 years before we had IoT and probably 20 years before we started to talk about digital twins. And so I think that idea was very misunderstood because in my view, semantic web is a parallel web to what we have for human consumption, but for machine-to-machine communication. And so obviously it doesn't require you to translate billions of web pages into semantic formats. Another one is the mixing up of the concerns. So as Martin correctly said, there were a lot of things that were wrong in semantic web, but people conflate the problems that the general semantic web had with the great particular ideas within the semantic web. And I consider one such very sad conflation is RDF and the graph data. So many things in semantic web could be wrong, yet some principles we should take and we should apply them forward. For example, a lot of people talk today about data mesh. It's a new hot topic if you follow the latest architectural trends. And mesh is essentially a graph which is quite regular in terms of its connections. But you can't build a graph without using graph technologies. And today we have data formats like JSON and XML and their documents, and computer science-wise, they're trees. And so they're not suited for representing graphs. I'm not particularly bound to RDF, but we need to have some format for representing graphs if we want to work with graphs. I think I'll end here with the with why semantic web failed. You asked also about OSLC. I have probably 3 reasons for why OSLC didn't take off particularly. I joined OSLC efforts in 2017, and I became co-chair a year later. For the years before that, a lot of players in the industry thought of this effort as IBM specific, and they were not keen on collaborating earnestly because they thought it was an effort from IBM with whatever business intent they had, which was not good for them. So Dassault and PTC, they were on the OSLC projects. I'm saying projects because the organizational structure changed over years, and now we're an open project under Oasis. They were there, but they didn't participate earnestly.
Okay.
Now PTC rejoined a few months ago as I was leaving. The second aspect is the domains, as you said, that requirements were covered, but a lot of other use cases were not covered. So right now we have the PLM domain work starting up. We just had the second meeting where we had, help me out, Judd, if you remember, I think we have Raytheon there, we have PTC there, we have IBM, maybe Saab.
Okay.
And so, yes, whoever is interested in that PLM domain is welcome to join. And the third reason, I think, is the openness. So we've been very open because we wanted to have a lot of flexibility. But as Eric was presenting in his slides, things don't work out of the box. And so half a year ago, we started to push for profiles in OSLC that would require more things from the vendors, and they would be profile conformant. And that should ensure that tools that implement a little bit more aspects of the OSLC to conform to that profile will actually implement enough to be interoperable out of the box. So these are the three reasons I think OSLC didn't take off. And finally, you were asking about indexing of information and querying it across multiple tools. In OSLC, we have an approach called TRS, Tracked Resource Set, which is essentially a persistent log that a server publishes of all the changes that happen to its resources. And the current approach, which is used, is to have a server that indexes all the TRS feeds from all the services, and then so some queries can be done on top of that. The only product implementing it commercially is IBM PLM. I think Engineering Insights is their product name. But the idea is very simple. You just consume multiple feeds, and then you can do analysis on top of that.
Thank you, Andre, for the answer.
Thank you.
So thank you, everybody. I think we should have a quick wrap up and reminder. So the workshop, I've just put it on the, I just shared it. It's Monday afternoon in Gothenburg. Our plan is to have small groups. So we'll split into small groups and we'll each discuss a topic. And then at the end of the sort of session on that topic, we'll have a summarizer who will sort of explain to the other groups what each one has come up with, and we'll basically go through the four groups, four topics that way. We'll have a coffee where probably most of the good work will be done as well. So I'll have a coffee break in the middle. So that's the plan for Monday. And I will share the recording as soon as I've worked out how to do it. David's already put his slides on the chat. I haven't PDF mine yet, so I will do that, and I'll share them with the recording. And I look forward to meeting you all on Monday.
Me too.
Yeah.
Thank you.
Thank you.
And don't forget to think about this all weekend.
Yes.
So, sorry, I can't be there.
I'll be coming.
Thank you all. It was really interesting.
Yes.
Thank you very much.
Thanks.
Thank you.
Thank you.